We are going to look at integration with partial fraction decomposition. And in this lesson, I will be looking at only linear non-repeating factors. And I am also going to do this with the assumption that you know how to do partial fractions. And if you do not, there are many videos on YouTube. I have one of my own, which I will link below if you need a refresher on how to actually perform partial fraction decomposition. So looking at number one here, we have 1 over this stuff. Anytime I have a fraction, the first thing I always check is whether or not the top is the derivative of the bottom. And it is clear that the derivative of my denominator is not 1. And so the natural log approach is out the window. After that, I see a polynomial in the denominator, and I want to see if that factors. And this one does indeed factor to 1 over x minus 2, x minus 3. So now for the partial fraction part, I will change. I'm going to rewrite my original fraction as such, and I know that that can be written as the sum of two fractions where one has a denominator of x minus 2 and the other has a denominator of x minus 3. And when you have linear, if I graphed y equals x minus 2 and y equals x minus 3, they are both lines and they do not repeat, which means I don't have something like x minus 3 squared. So when you have linear non-repeating factors, you can use a technique to solve for your a and b called the heavy side method. And heavy side is actually the name of a person. It is Mr. Heaviside is the one who popularized this approach. So Heaviside's approach says that if you want to solve for that constant a, you look underneath the a, and I have an x minus 2, and I notice that if I plug in a 2 for that, I will get 0 in the denominator. So I find the 0 of the factor under the a. I cover up that factor in the original fraction, and I plug 2 into all of the remaining terms. So my value of a will be 1 over 2 minus 3, which is -1. So I now know that a is -1. And then for b, I will do the same thing. I notice that if I plug in 3 to that denominator, I will get 0. So I go back to my original problem and I cover up the factor that is under the b. And some teachers call this the cover-up method for that reason. And b is going to equal 1 over 3 minus 2, which was 1. Okay, so I have performed the partial fraction decomposition, and now I can rewrite my original problem as -1 over x minus 2. And I'm going to go ahead and separate those into two separate antiderivatives. So I have -1 over x minus 2 plus, and then b, which is 1 over x minus 3. And now I have two antiderivatives, and both of them are easier than the one I started with. And if I have fractions, the first thing I look for is whether or not I can make the top the derivative of the bottom. And in both of these, I can. The derivative of x minus 2 is +1. That is a -1. So actually what I'm going to do is just take that negative out and put a -1 in front, which means I still have a 1 on top. And now my top is the derivative of the bottom. That looks like a -1. I meant to put times 1. There we go. And so this first antiderivative, the -1 on the outside, my numerator is the derivative of the denominator. So it's -1 natural log x minus 2. My second fraction, 1 over x minus 3. The top is the derivative of the bottom. Therefore, natural log x minus 3 is your antiderivative. And there is your solution to number 1, your general antiderivative. Moving on to number 2, another fraction. And again, I want to see if the top is the derivative of the bottom, and the derivative of x squared plus 11x plus 18 is 2x plus 11. I cannot easily make the top the derivative of the bottom. It could be done. There are tricks you can use, but I am now going to see if my denominator factors, which it does, and this one ends up being quite sexy. You don't want to just dive into partial fractions. You always want to stop and think about algebra or other types of algebra. I guess partial fractions is algebra. So I notice here that I have an x plus 2 on top and bottom. Those cancel. This one actually reduces to the antiderivative of 1 over x plus 9, which is quite nice because I did not have to use partial fraction decomposition. I now have a fraction where my numerator is the derivative of the denominator. Therefore, natural log of x plus 9. And there is your answer. Good, good. Cool. Now, as far as these antiderivatives, if you want to add an extra little step to make you feel a little bit more comfortable, this is technically a u sub problem where you would let u be the denominator. My du would just be 1 dx, and then you can replace the 1 dx with a du. My numerator got wrapped up in the du, so I'm just going to put a 1 up there to hold the place. My denominator, x plus 9, is u, and the antiderivative of 1 over u would be natural log of u. So all that stuff I just wrote in green is what I am omitting by just recognizing that the top is the derivative of the bottom. But if you feel more comfortable with the formal u substitution, you can do that. Moving on to number 3, 2 over x cubed minus 9x. Top is not the derivative of the bottom, so now I am going to see if I can factor the denominator, and you can indeed. That denominator you can factor out an x, and when you do that, you're left with x squared minus 9, which continues to factor to x plus 2, x plus, what am I doing? X plus 3, x minus 3. And I will partially fractally decomposite this. Just a little tip, whatever the degree is of your denominator tells you how many letters you will solve for in your partial fractions. So since this is x cubed, I know I will need an a, b, and a c, and that is pretty easy to see how that happens because I have an x plus 3, and an x minus 3. So I'm going to set that up. A over x plus b over x plus 3 plus c over x minus 3. And now we will use the Heaviside method. So under a is x, 0, we'll make that 0. I cover up the x and I plug 0 into all my remaining terms. So a is going to be 2 over 0 plus 3 and 0 minus 3. That's kind of ugly, but a is indeed negative 2/9. Repeat for b. I need to plug in negative 3, and that means I need to come over here. Hiccups, and I need to cover up the x plus 3. I cover that up, and I plug negative 3 into all the remaining terms. So b is 2 over negative 3 times negative 3 minus 3 is negative 6. That's 2 over 18, which is 1 over 9. Ugly constants in this one. And then we will repeat that for c. I need to plug in positive 3. I need to cover up the x minus 3 since that is what's under the c. Plug in 3 for all remaining x's, and my value of c is 2 over 3 times 3 plus 3 is 6. 2 over 18 does reduce to 1 over 9. And now I have a new antiderivative. I have 3 of them actually. I have the antiderivative of negative 2/9 over x plus the antiderivative of 1/9 over x plus 3 plus the antiderivative of 1/9 over x minus 3. And with that, I now have 3 simpler antiderivatives. I noticed that the denominators all have a numerator, a derivative of 1. And so I would like to see a 1 in the numerator, because if my numerator is the derivative of the denominator, then the antiderivative is natural log of the denominator. And I can make the numerators 1 by simply taking these ugly constants and moving them in front. Moving that in front. Moving that in front. So I have negative 2/9. And when I take that negative 2/9, my numerator becomes 1, which is the derivative of the denominator. I take out that positive 1/9. And when I do that, my numerator is 1, which is the derivative of the denominator. Plus, I take out that 1/9, and we have the same situation again. Numerator is derivative of denominator. And there is my answer for that one. Cool. All right. So these kind of get pretty repetitive. The linear non-repeating partial fraction problems are quite nice. See, number 4, check this guy out. Let's see, we have numerator is 4x plus 4, denominator is this. I'm looking quickly at my denominator, and I notice that the derivative of that denominator is, 2x plus 2. And if I can make my numerator that, then I don't have to do anything tricky, and we can the derivative of that denominator is 2x plus 2. If I multiply my numerator by 1/2, and so if I multiply by 1/2 on the inside, I need to multiply by 2 on the outside. This antiderivative becomes 2 times 2x plus 2 over x squared plus 2x minus 31. And my numerator is the derivative of the denominator, which means my final answer is 2 times natural log of x squared plus 2x minus 31 plus c. So you do not want to just dive into partial fractions because you may be able to factor the bottom or something like that. Always check for just a second, is it possible to turn your numerator into the derivative of the denominator? And if you can bypass quite a few steps. Let's see, I think I have 2 more. Is this the last one? Yeah, this is the last one. So this one's a definite integral. My numerator is 2x plus 2. Is that the derivative of the denominator? I don't know. Well, let's see. So if I expand my denominator, I would have x squared plus 4x plus 3. The derivative of that would be 2x plus 4. And no, you cannot conveniently make the numerator the derivative of the denominator. So I'm not going to do that. I will go partial fractions. So we have our numerator 2x plus 2. I feel a sneeze coming on. There it was. 2x plus 2 over x plus 1, x plus 3. And I will partially fractally decomposite this guy. And we'll use the Heaviside method. So I will plug in -1 for every x except for the factor under a. And I discover that a is going to be 2 times -1. Uh-oh. Something is not right here. Hang on. I need to adjust this problem because I'm about to get 0 for a, which is not supposed to happen. That's not how I intended this problem to work out. Am I going to get 0 for a? 2 times -1 plus 2 is 0. Okay, hang on. Okay, so I have now adjusted this problem. Let's just make it x plus 5 and the numerator denominator is the same. And to save you the trouble, the numerator is not the derivative of the denominator. So now let's go into partial fractions on this one. X plus 5 over x plus 1, x plus 3 is a over x plus 1 plus b over x plus 3. And before I go any further, my original attempt on this, I was going to get 0 for a. That's okay. It's fine to have a 0 for your a. That doesn't mean there's nothing mathematically wrong with that. It's just not what I wanted. So I wanted to revamp this problem to create a different situation. So now I'm going to solve for a by plugging in -1 for everything except the x plus 1. And we get a to be -1 plus 5, which is 4. -1 plus 3 is 2. So my a value is 2. My b, I need to plug in -3 for everything except the x plus 3. So let's do that. And b ends up being -3 plus 5 is 2. -3 plus 1 is -2. And b ends up being -1. So we end up with the antiderivative from 1 to 4 of 2 over x plus 1 minus the antiderivative. Actually, I'll do plus -1 over x plus 3. And that is also from 1 to 4. And when I do the antiderivatives, we once again have a situation where I need the numerators to be 1. So if I just take these things out, if I take that negative out and I take that 2 out, I will have natural log situations. So I have 2 natural log of x plus 1 evaluated from 1 to 4 plus, actually, you know what I'm going to do? I'll go ahead and write that. It's 2 natural log x plus 1 from 1 to 4 minus natural log of x plus 3 evaluated from x equals 1 to 4. And what I'm going to do to make this a little bit cleaner is, since I'm evaluating them both from 1 to 4, I could just do 2 natural log of x plus 1 minus natural log of x plus 3, evaluate that whole thing from 1 to 4, and it makes the simplifying a little bit easier. So let's plug in. Answer is going to be 2 natural log of 4 plus 1 is 5, minus natural log of 4 plus 3 is 7, minus, plug in the 1, 2, natural log of 1 plus 1 is 2, minus natural log of 3 plus 1, which is 4. Okay, so we have that. And the reason I want to talk about this problem is because in a multiple choice situation, they very frequently like to use properties of logs to rewrite your answer. And we could have done that on all the rest of them, but it really shows up a lot when you have only constants. We don't have x's anymore. And so some of the properties we could use here are the properties of exponents. I could take this 2, I can make it an exponent on 5. I can take this 2, make it an exponent on 2, which is going to make that right side quite nice. And we end up with the natural log of 5 squared minus the natural log of 7 minus the quantity of natural log of 2 squared minus natural log of 4. And if you look at this second couple over here, that is the natural log of 4 minus 4. That whole thing is 0. So that goes away. And we're left with natural log of 25 minus natural log of 7, which that could be rewritten as the natural log of 25 over 7. And so if it's a multiple choice situation, you have to be prepared to use these properties to match up to the options that are presented. In a free response situation, you want to stop as soon as you have numbers. And just to make a tiny point, we could have been using these properties all along. For example, number one, this is the same thing as natural log of x minus 3 minus the natural log of x plus minus 2. I could have written this one as the natural log of x minus 3 divided by x minus 2, and just be prepared to use those types of properties if the problem is multiple choice. And that is it for this one. That got longer than I wanted it to be, but whatever.